Okay, I think we can start. And it's a great pleasure for me to have here Professor Bjorn Engquist, which is a long-time friend. So finally, we got him in GSSI. It's really, I consider that a great achievement. Professor Engquist is an extremely well-known scientist regarding numerical methods and applied mathematics. He has been a long time also a fundamental member of the community of conservation law, although his interests are much wider than only the area of applied conservation law. But attending this community was the occasion that I met him. He was many years ago part of a European project that at the end of the 90s with some crazy people we tried to establish. But I have to tell you, it was very successful in shifting some balance of the field from US to Europe. And he was at that time also representing the Swedish mathematician on the Royal Institute of Technology in Stockholm. Professor Engquist has been for many years operating in UCLA in Los Angeles. Later he moved to Princeton, where he also remained many years directing the applied math program in Princeton, and to end up in Texas at the University of Texas at Austin, where he's still now. I don't know if you are the director or you are a member of this engineering computer center.
A member of the center there, director of some.
So the topic that is going, I have to tell you that the list of recognition that he got is impressive. I had to sign it here because I cannot remember. But he has received Science James Watkins Prize in Numerical Analysis and Scientific Computing, Peter and Risi Prize, George David Birkhoff Prize, and also he was selected by the Norwegian Academy of Science and Letters. So this is an incomplete list. So it is then a big pleasure to have here Bjorn talking about a topic that in life is pretty sensitive, is seismic imaging and optimal transport. So please.
Yeah, thank you very much for this kind introduction, and also thank you for the invitation to come here. This is my first time in L'Aquila, and it's great so far, so this is good. So I was connected to more to the European community earlier when I was professor at the Royal Institute of Technology also. And then I had engaged in a number of European projects, both on the academic and the industrial side. But this is a Texas problem, seismic imaging, and of course seismicity is important here. More for another point of view. The people over here, this is from seismology, a geophysicist at Austin. Brittany Froese came from the Monge-Ampère community, nonlinear elliptic problems, and that's where we started this on. And Yunan Yang was a student of mine that worked on this over there. She's now at the Curran Institute as a postdoc. And Froese is in New Jersey Institute of Technology there as an assistant professor. So I'll talk a little bit first about the original problem and the particular issue that we will discuss in this here, and that's why sort of the technology of optimal transport come into play. Monge-Ampère equation is essentially something that led us into this because we were looking at the numerical methods for that, and it is an application. Then it took sort of a life on its own, and we focused more on the seismic exploration part of that. And then we'll look at some examples and some of the challenges that are there, both when it comes to practical approximation and to the theory behind that. So the idea here is seismology, where the source is generated. So we are not looking at the earthquake so much, but a place where you have a lot of data, so you can actually more or less measure a function rather than just a signal. So, we have places where, for example, at sea, you will have a ship that generates a pulse over here by an explosion, many of them, and then afterwards you have a number of receivers, geophones recording, and they follow in a stream behind. So you really can measure a function on a grid. So what you get from that is then a pressure signal, in these cases, as a function of time, from all these different geophones that are hanging behind. And this is your input data. So these are a number of one-dimensional functions. And from that, you would like to explore, understand what is down there. And that means you would like to know the geometry, and you will also know the properties of the material down there. So we are thinking of this as modeling it as an elastic body, or a simplified version. And in the experiments here, we will just talk about it as a acoustic wave propagation, which is actually what the industry uses quite a lot today. Still, the data and etc. is a little bit too incomplete in order to get more parameters out that are needed in elastic settings. So that's sort of the initial challenge. And it is the difficulty here is from many of the other imaging principles like CAT scans and NMRs, etc., where the source to receiver goes through straight lines. X-rays do not bend much in the body. And then you have other principles of finding the material in between, like the inverse radon transform for CAT scans. You need a lot of data processing, but you have sort of a closed form of the inverse. Here, you have a variable velocity medium that varies quite a lot, and you have reflecting surfaces that plays a role for the medium that you have. And then it becomes a much more difficult problem. There are no direct ways of dealing with that. Traditionally, you made a coarse estimate of the velocities, and then you could predict the rays if you have the velocities, and then you can have more or less closed form behavior. Migration is a technique that was used quite a lot. You do a forward wave tracing, and then you do backward ray tracing, and you find the correlation is probably where there would be a reflection. That's sort of the basic principle over there. So now it becomes more or less the standard to go for a full inversion, meaning finding the parameters in the differential equation that represents the properties like the velocity, wave velocity in the Earth, which goes under the name of full waveform inversion. So that's the name of the game today. So the velocity is done by PD constraint optimization, and PDE here would be the forward wave equation. So that's the constraint that you're on, and then the optimization is to use that PD and match it with the data, and then of course you adjust the parameters so you get that match. So so we have a source over here, measurements over there, and you would like to find the coefficients down into the Earth. So there are a few steps where mathematics can play a role over here. So one is then how do you measure the difference between these two functions in a way that fits to the problem. And actually this is the one we will look at today. The other one is to have a fast wave solver, and looked quite a lot at that, and particularly then in the frequency domain where it's more challenging. In the time domain that most of the experiments are done here, the methods have stayed the same for a long time. Explicit time marching. You can change the order of accuracy, etc. But the overall principle, when it comes to the the domain solver, the Helmholtz equation is generically hard to solve, or the other version in ellipticity, because they are not positive definite problems. So preconditioning and all that becomes a challenge. So I spent a lot of time on this part here. And then the optimization, which here is more or less a standard type joint state method, coupled to a quasi-Newton method, and that has been settled more or less. So this guy here is what we will look at, the full waveform inversion and the measure of mismatch. The sound here, coming back, very rapid response here. On the system. So the idea here is that you have measured data on the surface, you have computed data that depend, in this case, on the velocity, and in some way you measure the difference. So this is some norm or some metric at least, and then you may need regularization, which hopefully in this is not so common over here, but it would be in many other problems. So this is velocity, and these are the measured data, computed data. And this is the standard choice that when it was developed, and whatever it is now, a couple of decades back, the first time, L2 has been used all the time. So that's the one we will compare with. So the reason for looking into optimal transport can be seen quite easily. So this is a traditional thing. From an earthquake, you get a burst of a signal, and then you try to match that up with a synthetic signal. Here, typically, it would be if you know how long time it took and you know where the earthquake is, you can get an average velocity, of course, along, if it is a Rayleigh wave, along the surface of the Earth. And the other way around, if you know roughly the velocity and the timing of the event, you have a couple of measurement stations, then you can find out by triangulation where it is. And here you obviously see where the signal is. You could use that also in an inverse problem in order to match these two things up. Of course, the difference between them then would play a role in this case. And one way of measure these things is to use the theory of optimal transport, which does measure the difference, you could say, between two probability measures in this case, or positive functions in this case, with the same mass, by estimating the work done to move this mass over to the location of the other area. And in computer science, where it's used both in image reconstruction and in machine learning as a distance measure, it's called Earth movers distance. And this was sort of the early Monge did, and then Kantorovich expanded it in a more abstract way, so it's usually called Monge-Kantorovich problem. The thing is, if we have this case over here, it's easy to see from a seismogram, measure the distance. Typical signal in exploration geophysics is, so you need some more intrinsic mathematical way of comparing signals that look like that, where you cannot sort of click on where the pulse is coming. So therefore, we thought about this being a more mathematical way of comparing something with a distance involved. So the Wasserstein distance then is a metric between two probability measures, or measure with the same mass. And that means that you take the lowest work measured in the following way. So this is a metric for the distance moving from X to Y location in one measure to the other, and you over the product measure sitting on F and G in this case. So you minimize overall combinations in X and Y and the distance point over there. What you need is that the mass is the same. You are supposed to move everything to the other place. And of course, the measures should be probability measure or positive measures in this case. Here we will have signals that should be positive and have the same integral. It's a better way to do this if you're dealing with function, and in this case, or easier way to think about is that the infimum of the Euclidean distance between the origin and where you end up in G, that's the distance you move the mass, and this is the amount of mass, of course, that you move at that distance. And T is then a function, and you minimize over all of those. So you take the least functions. That's a good measure that can be used when the masses overlap or when they are far apart. So the distance here, if you take, let's say, shift is a natural movement, because if there is a change in velocity in between the source and receiver, what you get, of course, is that you arrive faster if you have a higher velocity. So it's there are many distortions, of course, of the masses, but shift is a natural one to look at. So we have, let's say, one signal here, which is shifted a little bit, and there, in this case, what the Wasserstein distance does, it takes the distance of the shift, and then you square that, the W2 distance. And then you multiply, and you measure this squared here with the mass that is moved, which is order 1 in here. And in L2, of course, takes the square pointwise. So this integrates with this arrow over the support that is down over here. And they are quite similar. They're the same order in this case. So then they're close up, they're the same order. What turns out that using the L2 difference, when they are further apart, when you don't have a good starting model, it doesn't work well. It's called in the business cycle skipping. You hit the local minima in this minimization. So if you are far apart here, the Wasserstein distance is still large, so it is the distance in this case when you have taken the square root usually, but the L2, when they are far apart over here, the difference here is just the L2 norm of this and the L2 norm of that. So you take the L2 norm of this minus that, and then of course they are not overlapping, so you just get a sum. It doesn't change with time. So if you look more at the signal, so this is what they call a Seismic, which is the second derivative of a Gaussian. So this would be a function looking like that, and it's a little bit like that's sort of the academic version of a seismic signal. And you would compare how the difference between the blue and the red dashed line is when you have different shift, that is different average velocities coming in. So if you do that, here is just an argument for why it's natural to look at that. Your shift is a function of t. You just change this guy, or dilation is stretching if you actually have the velocity change where you're measuring it. So shift and dilation are natural type of mismatches that appear in this case. So if you now look at the L2 norm of F minus G, or this signal minus that signal, of course, when there is no shift at all, they overlap and the difference is equal to 0. So here is the one we are shooting for. That is the minimum of the L2 norm in this case. But if they are a little bit further apart, they either positively or negatively cancel out, and you get local minima, and you'll get barrier there. So an optimization routine that would like to minimize this function, you have a risk of hitting these ones before they come to the true one there. And also, as we said before, when they are far apart, then the L2 norm just measures the L2 norm of the two different ones without seeing anything, so you don't get the minimization. Now, if we, on this thing, use the Wasserstein distance is actually squared. This is the one we use. And the same to here, it's L2 squared in order not to have lower regularity. It's just a perfect parabola. So it's very good for imaging. Now, of course, the full problem is more complex than that. But this is the heart of why we actually started to look at this way. And methods for the L2, for let's say, convex optimizations are very, very easy. So the local method takes you to the global mean in this simplified setting, but also works very well in practice. But there are some difficulties that I'll come to later there, so the theory is not as clean. So if we're going to look at this problem now, so we agreed upon a little bit that in shift and dilations are natural things to look for, that you would like to have convexity, and that one can prove in this case, so that this is convex with respect to translation, S, which is a shift distance in arrival time. So if the F is just a shifted part of the signal of G, or maybe dilated, so you stretch it with a parameter alpha, or compress it with a parameter alpha. So in this alpha S space, it is then convex. You could also look at it convex if you do take a local change. You take originally this part here, you take a small support in there and let's say add a constant, or stretch it with a parameter, as was done over here. You have to compensate because the mass should be the same, so therefore it has to be different also there. You can then show that it's convex also with respect to dilation, to local perturbation, sorry, in this case. That's also true for L2. This is not true for L2. And in order to there is a development, of course, a lot of theory. Recently, it was reactivated, this old idea of optimal transport during, maybe first by Jan Brenier, when he connected it to the Monge-Ampère equation. A lot of convexity result came, and then people like Villani has, and then afterwards, together with also developed here in the French, Italian school, I should say, optimal transport as a big thing. Was also part, actually, of the latest Fields method of Alessio Figalli, did these things. So it's a rich topic in theory, and therefore there's a lot of things developed, like the analogy with C-cycle monotonicity, a lot of monotonicity results that one can use to prove these things. So I'll look at sort of poor man's version of this, where we just have a discrete power mass. Then you have to do it in a more functional analysis setting in order to do it well. So let's say we have these blue points, that is one of the sets, and the red points is the other one, and they are connected with a shift. So every blue point, it moves over here. Now you would like to see what is the optimal map here. Is this, if you compare this set of points, F, and this set of points, G, if you compare them, will the Wasserstein distance in this case be S square, the quadratic square in this case, which we wanted for the convexity. Maybe there is a better way of doing this in the optimal transport way, that you transport it in this, for example, of course, is much shorter than coming from the original part over there. So one can do this, and then here you can do it explicitly on the back of an envelope, as we typically say. You just expand what it is, and there you can describe then the map by a permutation, which mass goes to which other mass in this case, if you expand this, and then use the fact that the sum of the masses are the same. So this term here goes away, and you're just left with that. Here is the S square term, and the best you can do is to do the permutation identity here, so that these guys cancel out, and then you have the S square. So in the general setting, it's messier, but that's at the heart of these things. So you can also generalize this dilation, so you can actually multiply with the matrix if it's positive definite, and then it's quadratic, it's convex in terms of the eigenvalues. So that's sort of a good background mathematically. So that tells that at least in these idealized cases, it will work well. And there's one inequality I didn't know I had that coming, that was used for these local change in variable. Typically you would have, of course, not perfect signal, so you would have differences coming in. So a perturbation like that will still be convex and be adjusted for. Another thing is that the signal measurement, at least G here, is noisy, and a good thing with optimal transport is that noise is not seen so much by optimal transport. So if these are the same signal here, G is just equal to F plus noise, and noise is of order 1, like say, can be uniformly distributed random numbers of order 1. Then the L2 norm is also order 1, because that's the size of these difference from 0 over here. The L2 norm is then, if this is the discretized signal here, so we have n points in this, is then 1 over n, because it doesn't cost so much in the Wasserstein distance to move, let's say, a positive part of the noise to a negative part of the noise, because the difference, if you have not too long, if there is a weak correlation, let's say, between them, they would sit very close together, and when you move that, it cancels out. And that one can do just looking at statistic method to see that it is of this type. So it's very insensitive, it's robust versus noise. So these are the two things that goes into the signal for being well. So why we started with this was then that it was earlier not a good idea to do this, because the techniques in order to find the optimal transport, or rather the Wasserstein distance, measure optimal transport in higher dimensions, and this at least 2D here, we see it was quite high. In 1D, it's just sorting comes in. So there it's n log n. You have an explicit formula for that. In higher dimensions, there are these combinatorial methods that grow with a number of unknowns quite a lot. And for a seismic image, we typically have in the hundreds of thousands to millions of unknowns in order to describe the material, or tens of millions. So it's quite large. So it's not possible to do that. But now there are sort of order n algorithms, and the earlier ones, at least, they were based on the Monge-Ampère equation. So the idea is there that we had the Wasserstein distance, where we tried to find this map T, mapping from F to G, that minimized this metric over here. What Bernier showed there was that you get that as the solution, or the gradient of the solution to a Monge-Ampère equation. So here is a nonlinear elliptic equation with the right-hand side that comes in for these things. So that's sort of where we started off in doing these things. So the Monge-Ampère equation looks like this, the determinant of the Hessian over here in 2D, for example. And also there is a good scientific foundation of the viscosity solution, starting with the Crandall-Lyons in this case, and then using monotone approximations the first time. Then Guy Barrel and Takis Ogenidis proved in the earlier of the 90s that if you have a monotone solution, you can get convergence to the viscosity solution. So you do the same sort of viscosity comparison type of thing discretely, as was done in the continuum case over there. And then this Brittany Froese came to us as postdoc. I thought, so why don't we apply? And she had her thesis based then on one particular way of deriving a monotone scheme. And I, before, looked back to the type of nonlinear conservation law where we looked at upwind differencing and Weno and Eno type schemes, meaning that you changed your approximation standard in a nonlinear way depending on the solution. And it's the same thing here. But here it is to get monotonicity. Also there, monotonicity plays a role for convergence. And one way of doing that is to do the derivative not by a standard sort of finite differencing derivative in the x and y direction, but allow for including then differences in different way using this formula for determinant of the Hessian that exists in terms of the eigenvalues, and do an approximation in these directions that comes from the eigenvector. Now you use finite number of them, so you don't stretch it out to a continuum because you are living on a lattice, but that's what they did, and that is a technique. One could modify it a little bit by multigrid and smooth out, etc., in order to do convergence, and then you get methods that converge for the monotone scheme. And as also is done in conservation laws, even if a theory typically applies in a clean sense for convergence for low-dimensional scheme, monotone, or entropy conserving, then you can use perturbations of those of higher order to get that. And the same story is valid over here. So the idea here is now to go to see what happens when we are try to meet go from this theory and meet the real world in the approximation. And we're thinking of two types of problems. So one is this inverse problem that I mentioned before, and this is the one I will focus on over here. You can also think about registration, which is comparing two different sets of data and see what is the change in there. So I'll just make a remark of that. And the convexity property was the one driving that you, instead of L2, you would have another way of measuring the mismatch between the computed data, which you adjust, and then the given data, with or without noise in this case. So the first experiment was done just by using ray tracing. So you think about an experiment, you have a source and a couple of reflectors, piecewise constant materials over here, and here is time, and here's the offset, meaning the difference between source and receiver. So you get, of course, the first reflection coming back faster, and the more distance it is, the longer the rays have to travel, and then you get a later distance here, and here you have the other one doing that. And then we took sort of a generic inverse scheme to do that. If you'd use L2, the surface in two of these 4 dimensions cut looks like that, and with this Wasserstein distance, it's much cleaner, and you can easier converge to the global minimum with using a standard minimization. I think this was a simplex method of Nelder and Mead that we used in this case. In order to do so later then, when student also joined, Yunan Yang, us, then we changed into methods that would fit for a much larger number of unknowns. And this would be the joint state method. So you need to calculate the gradient with respect to the unknowns, all the different C values. You need the Fréchet derivative of the functional, which is a Wasserstein distance, with respect to the unknown function, C in this case. So you need to calculate this, which in the L2 case looks like that. And this is what people have done, this functional here, where you take the Fréchet derivative with respect to m. Here should be lowercase m, the same one there. And then you can do this, of course, with the chain rule in this case. It is a bit messier for the Wasserstein distance. It looks like this, so you can still do by a perturbation argument. You linearize the elliptic equation, non-linear elliptic equation, and you get an expression where you can measure all the terms in there in order to do that. And a joint state method means that you correlate sort of a forward source that we have, and then a backward residual. You go calculate forward in time and backward in time, which corresponds to the solution there. So it's like back propagation in machine learning, for example. Well, there is a difficulty which I've swept under the carpet all the time here, and that was the restrictions on the Wasserstein distance. These are probability measure of the same mass, and also they need to be positive. You're not allowed to cheat by getting a lower value by transporting negative Earth. Or dirt in this case. And of course signals doesn't look like that. They are wiggly things, and the natural thing is to have sort of the zero pressure being zero, and sometimes it's lower, sometimes higher. So you need to modify your solution in order to fit to this requirement, which is reasonable to do that. So let's, anyway, before coming to this, see what we can do with initial tests. So this is sort of the benchmark problem that is artificially made up to look like a seismic structure, where you have layers, fault lines, different types of material. It's a Marmousi model that's always test, and you start with something that doesn't know how it is, but typically have a little bit of geophysical interest, like, for example, the velocity increases when we go down here from low velocity a little bit higher to do that. And if you then use, this was a true velocity, use the minimization, and in this case, adjoint state measure for the gradient, put the gradient into a quasi-Newton method, and then run that for some time, 100, 200 iterations. It looks like that, and we have required quite a lot. The L2 way of doing this require much better starting values. Otherwise, you get trapped in local minima, meaning that you miss a lot of the feature in doing this. So this was quite astounding in a sense, and now industry is adjusting and coming back. See there, that's the life. Anyway, so this is a good point. Here, the normalization was quite simple. That is, this is could be positive and negative. Let's add a constant, so it becomes positive. And then you normalize by dividing by the total norm, so that the mass is 1. So this, even this did quite a good job in doing these things. So let's do, when we're doing this, remark on another side benefit of calculating the transport map. That is how, where, if let's say this is one image and this is another image or seismic setting, and we would like to know which piece here is moved there. So this guy up here is moved to this one, this guy is moved to that one, for example. And then we would like to see how it moved. So this map here tells with the arrows pointing how this was moved. So you could sort of measure the change and the direction of the change between two different seismic settings. And this is used in order to compare, let's say, one way of measuring the Earth with another way. It could be that you have a seismic image, but you also in certain places can drill and actually measure the properties directly from rocks that you bring up. You could also, reservoir modeling, you would see when you, let's say, carbon sequestration, you try to pump in carbon dioxide in order to save the Earth. Or you could pump out gas in order to destroy the Earth, and monitor this process in a way that is measurable. Know what changed in the geometry. This is still needs a lot of fiddling around, because it's not so easy. If one of them changes mass, then you have to transport mass between them, etc. So one has to do a lot of fixes in order for this to work. But in principle, that's also something that would be useful. So let's go back to what we can do for these modifications that we didn't have. One way was doing this linear change, which actually worked quite well. Another way could be different other normalization to bring sort of a general signal to a positive measure in this case. What turned out also during the experimentation is that very often it was enough to do 1D optimal transport, just use time, instead of the full 2D. And then you have a closed formula, as I said in the beginning, just n log n, sorting algorithm, which is easy to do. And in most cases, if you adjust in one dimension, you adjust it also. And this, of course, the industrial application likes, because it's a fast, and you don't have the numerical errors with the Monge-Ampère equation, even if that was the one that triggered us. So most of the applications were then done trace by trace, as we say, is 1D. That's also very common in computer science, that you do sliced Wasserstein, as I say. You do a number of 1D in order to build up an approximation of the 2D version. So in 1D, then the difference here is closed form in the sense, so you take the primitive function of f and g, let's say in this case. First you normalize them so they are positive, and that is a primitive function will be monotone in this case. And then you can bring out f squared, so or the inverse of f, where f was the primitive function of f, and capital G the primitive function of g. So you could think about this one as a way of doing it. So you have a closed form of measuring the distance, an easier way also than to calculate the derivative, the gradient in this case, the Frey derivative of the Wasserstein distance with respect to the unknowns. So you have also there a closed form that is more robust, because you only do integration and you do inverse of a function, rather than needing to solve a number of the PDEs on the way. So the normalization, we tested many ways of doing this to get this property, and it's been also done in others by literature. You could, for example, first of all, you always in the end normalize it. So whatever you produced, you would then divide by the integral, so you get the integral 1 over here. You could square the signal. You could take the absolute value, you could do the positive part and do positive or negative part. All of these actually turned out to be give troubles for different things. For example, the absolute value and the positive part are not regular, and that gives difficulties in the optimization regime, and in particular if you would like to solve it with a Monge-Ampère solver. So that is a major difficulty. This is not one-to-one, so you can have a match of F2s, but not F itself. It could be positive or negative. And this was then the one that we mentioned before. The difficulty with this guy is that all the other ones give nice positive, the convexity theory works over here. It doesn't do here. If you add this constant over here, you get a reduced number of minima, or they are smaller, the local minima away from the global minima, but it doesn't do the convexity. Well, that was sort of the holy grail we started with, that we had it with respect to shifts over there. So now one can do a compromise. One can use an exponential function which adds and add a constant. This is a monotone with respect to f, so you can take the inverse and all these things we mentioned. It's one-to-one, and then the exponential here makes it never be negative, even if f is negative, and then you might also add a constant, which I'll mentioned a little bit before, in order to make it even better. So here is a little bit the difficulty of the other way. So this is a way of normalizing that keeps sort of the good property if the alpha is large enough, and still doesn't have the negative of squaring or taking the absolute value. So here, what it looks like, you sort of suppress this part, you have a larger part here, and then the function at least is convex with respect to shift. So this is the same simple test we did before. And again, I should say that for a full general problem, we're not talking about just with respect to convexity of one variable, one we have hundreds of thousands. It is not a perfect convexity thing, but much closer to it than if we have the L2 norm in doing that. So even if you have positive measures to start with, it could still be good to add a sort of layer of constant over here, so that F would be this signal there plus this buffer region, G would be that signal plus this buffer region. And that is not mathematically directly seeable, but it's practical. It will be some Huber norm in the sense that if the F and G are close together, you would have this convex behavior. The further they come apart, you would have more linear behavior there. And this means that events that are far apart, that typically wouldn't be things you should compare, because it's signals that came from very different parts of the Earth. So it's sort of not the matching you would like to do. And therefore you don't want this to go up and be overemphasized the way. And this linearity, one can prove, comes because now instead of moving all the mass from F to G here, you move a little bit of the mass down to this buffer region, and then you move it up to G. And this moving down and up will be more and more stressed the further they are apart, and in the limit they will be linear. So that actually turns out to be a useful part. Also, increased regularity. So this map that we had over here will then be continuous, and this means that the Fauché derivative will also be continuous. This functional will be C1. And that's not the case if we didn't have that, if these were just two portion math. Let's, for example, think that F looks like this. G is here, but a little bit of G is on the other side. You have a measure there and a little bit there. That means that part of F would move there, but this little piece here will move in the other direction. So somewhere in the middle here, you would have a jump in G from moving it to one side to the other. Now, if you have this buffer region, it doesn't happen. It sort of makes it continuous. And of course, depending on how this function is, you could be higher regularity also. So these are mathematical properties that made it even better than in the earlier setting. Oops. So with this, one can redo the thing. It's on the eye, looks very similar to the other. But when this compares, actually, first I should say that this compares the trace by trace, which actually turns out to look better than the globally using Monge-Ampère equation. And that is, of course, that trace by trace was just a quadrature. So you can do that very highly accurate. And a Monge-Ampère solver, it's a difficult elliptic problem. And therefore, you have errors in the calculation. A better solver would probably do much better than the one we had in there. And you could also do problems that have very large contrasts. This is salt, which often traps carbons. And with the Wasserstein distance trace by trace, you can sort of find it fairly decently. If you do a Monge-Ampère solver, you also do a good job, but then because of the discontinuities and almost vacuum in a sense for the Monge-Ampère solver, you get into difficulties. So it's a challenge to do that, but still it does better. This L2 misses a lot of the properties that is in there. If one can also do a sensitivity to noise, so this is a quite large noise. You see the original signal is sitting there, and then we have additional noise with a weak correlation, so we take local averages a couple of times, not to be too favorable to this, but the solver doesn't see that and reproduces a little bit blurred, but otherwise very similar picture to the Marmousi model that we had in the earlier setting. So one thing that we found also where this was much more successful than using the industry standard before, which was L2 norm, was that even if you have this setting over here and get reflection in this surface, What is below this surface, let's say we have a reflection here and we don't get reflections below because we don't measure so much time, or rather that there is nothing like that. We can actually get information from down here even if there is no signal coming back from there in the measurements. And that was a little bit striking in the beginning. And also, in order doing that, it seems sort of counterintuitive. But we could do that. So if we do this thing, so let's say this could be a water layer. This is a layer where we know what it is, and we don't know what's here. We don't know anything about this. So our starting model is this. We have no idea what it is. Of course, the true seismic data has a reflection in this layer. So therefore, when we start to do the inverse problem, a reflection builds up over there. If we now continue to do iterations based on the same thing as before, we use a Wasserstein distance, we take the Fauché derivative, we put it into a quasi-Newton solver, blah, 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 blah. If we use L2, it stays there. That's what you get. You get sort of the reflection, but you don't get what's going on down here. But if you do W2, you actually start to fill out this layer, even if there is no information coming back. And of course, no information coming back is also information. It tells that there is no layer down here, or there is no change. And what you have done is that you create this first layer here, because there is a reflection, so the gradient has to adjust to that, and you find the reflection and you get this layer. And now, when you do compare further, in your model, there is this layer that ends, but in the true model, there is no. So there is no secondary reflection or mixture over there coming in. And that is noticed by the Wasserstein metric, but not by L2 in this case. So it looked like that. So you create this, and then you start building up, let's call it mass on the back side of the reflection in S over here. This is a very weak reflection because it's not a discontinuity, it is a discontinuity in the derivative. And a weak reflection with the L2 measure is squared and become even more weaker. In the W2 it's not squared, so what you square is a measurement, S here, the shift, and as large, when this becomes larger, then you emphasize it more. So when you minimize, you drive down the effect of this reflection. So the L2 converges very rapidly because you don't see this guy, and therefore it stops, more or less. And the W see this reflection here, and also the return on the variable coefficient, and therefore this drives down the value, or rather S, you have to go to much, much larger S to come within, let's say, convergence in the setting of this thing. And that's why it's one of the things. One can also look at the difference on the frequency contents on the reflection, where this is lower frequency than what L2 does, because this involves an integration. We had the capital F and capital G involved there, and then you can fill that out. So that's a drift. So that means when you apply it to something where there is salt, where the reflection is very much important, and there are no sort of waves that penetrate directly over here. If you take initial velocity that doesn't contain the salt, but the other structure roughly in there, then again, when you do a few iterations, you start building up the surface. The L2 also does this here, but then you continue with a number of iterations. You fill out this over here in the W2 sense, but not in the L2 sense. You get back the salt to a much larger extent, and also the structures below will then be seen because it behaves physically in a more correct way. So that's the part of it. You would say that the optimal transport was a tool then that in this case it turned out to have many features that were practical, like the convexity and like the sensitivity to small events. like the reflection at the bottom of this layer. The good part is that some of them are connected to the theory of optimal transport. You can prove certain things about it, but of course, for the practitioners, it was more important that you can see that it also works when you apply it to real data. So afterwards, a number of groups have started to present that, in groups in France and in the United States in particular. They use either, because they have now the fast ways of calculating the Wasserstein is in both the W2 and W1, where you use the L1 norm rather than the Euclidean distance to take the distances, are used in these and presented at this exploration geophysics meeting quite a lot. And also industry adapted it, and so there are field data presented by different companies, in particular used in the North Sea. And I have no results from that, and therefore we can record this. Otherwise, it would not be possible to do that if there were real field delta where there is some void. So one could look for further refinement, maybe to unbalanced optimal transport techniques, which wouldn't then be requiring the same amount of normalization. It would at least allow for different norms. Of course, when you do renorming, it's a way of doing one version of unbalanced optimal transport. And then the major thing is, of course, that now with more high fidelity data, it would be possible to have models that are closer to reality than what the acoustic model is. And the industry is trying to do that in different parts where it's important. So ideally would be a full viscoelastic model. You could also think about an improved acoustic model where you have inhomogeneous material, layered material, will then create different velocities along the layers and across the layers. So it's not isentropic velocity propagation. That is also one way of going. So this would be sort of natural things in the future. Otherwise, it's a fairly good balance between the theory and the application. In this case, it's not always so in applied math. Thank you very much.
You make these compromises at the moment just because otherwise you lose convexity.
Yeah.
And then it seems that this also helps you to get some regularity from the model.
That's right. And particularly adding this concept gives regularity. Yeah, you got to run, even if you think about the, and here it's easy to see in 1D because you have explicit formula, so you can go in and see that directly. The other one, again, would be the places where you lose ellipticity in the Monge-Ampère equation. So these are the places which cause trouble in the solver there, and that's where, of course, the
is regularity in Monge-Ampère really an issue for the algorithm?
I don't know directly, but if that is because there are so many components that floats around, but it could certainly be. It could be that the lack of regularity would then transfer into difficulties in the gradient descent method in the nonlinear or in the linearized Newton solver. I would be. So it's certainly so if you have problems with in conservation laws, and I would here is one order smoother, but still, I mean, it could be problems, I think. Okay.
Okay, good.
Just not really a question. So there has been recent work trying to define generalizations of Wasserstein distance to include the spatial inhomogeneity of the domain. So I'm wondering if it might be worth building a system that has a feedback or an adaptive Wasserstein distance that takes into the account what you have already learned about the region you are trying to describe. The theory is rather new, is only 5 or 6 years old.
Okay.
I don't know how much is. I know some stuff is done. It's proved that it's a consistent notion of distance, say, so anisotropic Wasserstein distance, something like that. Maybe it can be useful in applications.
Certainly. I don't think I know of that.
The key name is Lisi, Stefano Lisi.
Okay. Well, where is Korean? Okay. Yeah. So there a couple of comments there. The first one is that through this process, of course, we saw that one had to do in its purest form. It doesn't work. First of all, it doesn't match because you need to normalize in some way, and secondly, in its purest form, you have this lack of regularity. You have a few things. So then we added a layer, and then of course it's not fully optimal transport because you can transport into the layer and there. So even if you write it as a transport problem, it's not the original one. So the metric, when it comes to seismology, can certainly be improved by fooling around with a clean optimal transport setting. So in that sense. The other is, of course, that would be good to look at. The thing is, of course, that you would think of adding the information of the unknown, the C here, in this case, in between sort of event. But what we are measuring is the difference in arrival at the surface. So it's not directly correlated to the, it is in a very implicit way correlated to the properties of the Earth, the inhomogeneities that you mentioned. But of course, there is a correlation there. So even if one has to understand how that maps into how one should do that. But yeah, that seems reasonable to look at. Thank you.
Mentioned some noise filtering as a byproduct of the algorithm.
Yeah.
But essentially you can somehow clean up with respect to background noise.
Yeah, it doesn't see noise so well. That's right. Yeah.
Do you think that some what modernly is called the machine learning style algorithm could be used somehow to teach the algorithm to learn to clean up noise?
I am not sure about that, but certainly it's possible. I mean, one shouldn't rule out the possibility of using machine learning in ways. Let me have one point there. The noise I've not thought about, but the one, if I go back, I think it's the only way of going like this here. There. This one here, it's rarely as clean as this, and I mentioned that we were not as successful over here as alt. This kind of comparison, I think, would be better done with machine learning than through this way, because there are many features, small features that are obviously seen by the eye. Seeing that this piece here has a certain structure and that ended up over there, which machine learning is very good at. And we use quite a lot in interpretation in seismology. So now at these meetings, there is a sizable fraction of machine learning. One thing that is done much better is if you have a fault lines over in the neighborhood here. So you have typically sedimentary layers that's created through the millions of years when it was sea bottom. And then you get a fault, so they shift. One way of measuring how much it is to see, take a layer on one side and then see where does that continue on the other side of the shift. That is something that's done by experienced people in geology. See, this looks like it continues over there. Very hard to put a mathematical way of doing it. Machine learning is excellent in doing this, because you can see on one side, you can learn because there you have continuity, so you can learn this intrinsic structure of the different layers over there, and then apply it on the other side and see how it was shifted. It's done very well there. So there are certain niche sections of these seismic inversion where it plays a role. To try to do wave propagation is, I think, stupid. It's such a well-defined problem, and there are such excellent algorithms to try to learn all possible variants there. I think is insane. But there are places where it plays an important role, I think.
Other questions? If not, thanks again.
Thank you. Okay, good.
So do you have your key or?
No, I got it back, so it's all yours.
This is
Yeah, this is one to this guy.
You know that this guy searching the way, okay, he left here his key, he took it.
Oh, I see.
That's yours. He told us it's a percentage, but it's
Yeah, sure, yeah.